Alright, so in this PowerPoint, we're having the ECE 1304 color matching project controlling RGB LEDs with the 74HC595 shift register. This is at Texas Tech University Whitaker College of Engineering, and our group is Dana Arnold, Iman Ahmed, Megan Howell, and myself, Colton Hendricks. My part of the project was to research the RGB LEDs and how to configure them. In this project, we are using the RGB LEDs, or red, green, blue, with 3 pins indicating the colors. From left to right, the 4 pins read R for red, common or ground, which is also the longest pin on the LED, G for green, B for blue. The LEDs are powered by a series of binary numbers in groups of 3. So for example, red is 100 and blue is 001. When these are combined, you can create purple, which is 101. And all of these LEDs are controlled by 32 bits, which are coming from the 4 register IC outputs.
I'm Iman Ahmed, and I designed the schematic for the project. So here we have the Arduino. We have 10 RGB LEDs, 5 push buttons, and the most important part of the project, 4 8-bit shift registers. The shift register is really important here because we're getting multiple outputs from each of the shift registers just using a certain amount of pins from the Arduino. Since there are so many nodes that need to be connected, we would have run out of pins from the Arduino. So the shift register has 16 pins, 8 output pins, 5 control pins, 2 power pins, and 1 extension pin. Pin 1 through 7 and 15 are outputs that go into each node of the LED. Since we're using RGB LEDs, each LED has 4 nodes, 1 to the ground, and each of the other 3 are used to light up a specific color. These 8 outputs are going into each node of the LED. Pin 8 is the ground, pin 16 is the power, pin 13 is the output enable. It needs to be on for us to basically get outputs that would turn on the LED. It's active low, so it needs to be connected to the ground to enable it. 3 really important pins that are going into the Arduino are pin 14, which is the data line pin, and it puts the value into memory, either 1 or 0. Pin 11 is the input clock that shifts data into memory. Pin 12 is the output clock or latch pin, and anytime it is triggered, the data in the memory is copied onto the outputs. Pin 10 is the master reset, and it goes into the Arduino where the user can use it to clear the memory through the code. Pins 10 through 12 from every register are connected all together that go into specific pins onto the Arduino. Pin 9 acts as an extension, and it goes into the data line pin of the next register, and this happens with the next register and happens with the next register, and then this makes all the registers act as one single thing.
Hi, my name is Dana. I was in charge of putting together the circuit as well as programming. So I'm going to show you a little bit of a video to demonstrate what the project was about and what we did. So the off button turns off all the LEDs, and then when the user types in, let's say red, the LEDs turn red, blue, white, etc., as well as rainbow. I added rainbow as well. And then I added a few patterns like flash and rainbow road, which has rainbow and then it turns on and off, and it just looks like a cool pattern. I'm going to skip through these because the video is kind of long. But I will show you how I use buttons as well. So the first button activates Rainbow Road, and then the second one activates, I think it's Flash, Flash, and the third one, if you press it, it's red, and then purple, rainbow. I think I added 5 buttons to the circuit as well. So you can see that it pretty much interface, it shows you which button is what. And then I'm also going to show you the code as well. This is the code for the project. The code was way too long to even fit on one slide. It's around like 300 lines. So I just will show you that in MATLAB. So this is the code that I used to pretty much make it so you can have red, which signals the lights to turn red, and all the different colors as well as patterns. So I used digital, which makes it so I can control each node a lot easier. So let's say you wanted red, I would do 100, 100, and so on. And then for the buttons, it was pretty easy to do because let's say I wanted one button to turn on. I would just have to say, okay, that button B1, or whatever I put for the digital pin, that one would be 1, so, and then the rest would be 0. And then I would just did an else if statement to pretty much say, okay, I want purple or blue or rainbow or whatever color I wanted. And then it was the same for the user input as well. I just said, okay, if the user input is yellow, then execute yellow and write that to the register. So that was pretty much the code, and then the only difference too was I added a reset register, which pretty much just wipes out whatever is in the register and then turns all the lights off.
This is Megan, and I did the research behind how to make the buttons work. As mentioned previously, many parts were used, such as an Arduino and shift register. However, buttons were used as an extra component. Buttons are used to send a signal to the microcontroller to tell the LEDs what to do. In our project, the 5 buttons control whether the lights turn on and off in rhythm, rapidly blink, or turn solid. In order to make the button work with what you want to happen, you first have to declare what this will be in MATLAB code. Once specified, you hold the button down for 3 seconds. The button will then send a signal to the shift register, which sends a signal to the LEDs, causing them to do the desired function. For example, when the LED lights blink, there's a slight difference between each color. This is determined by the pause function in our code. This also happens when the light changes in rhythm. You first need to declare button in MATLAB so that it knows that the button will be functioning. Then you need to declare either a color, which can range from red to purple and white, or commands to make the lights blink or go off and on in rhythm. You can also turn the lights off by saying off in MATLAB. And this is a list of our references.